NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we solve systems of the form fraction of a linear expression in the denominator. We will convert them into a first-degree linear system using a clever substitution, and then solve a concrete example. Here is the structure. Each equation is a sum of constants divided by linear expressions in x and y. Notice the repeated denominators, bx plus c and b prime y plus c prime. The key trick is to substitute the reciprocals of the denominators. Let capital U be 1 over bx plus c, and capital V be 1 over b prime y plus c prime. Then each equation becomes linear in u and v. Let us practice on a specific example. 2 over 2x plus 1 plus 3 over y minus 2 equals 4. 5 over 2x plus 1 plus 1 over y minus 2 equals 3. Define u equals 1 over 2x plus 1 and v equals 1 over y minus 2. The system becomes linear. 2u plus 3v equals 4 and 5u plus v equals 3. Now solve this 2 by 2 system. From the second equation, v equals 3 minus 5u. Substitute into the first. 2u plus 3 times parenthesis 3 minus 5u equals 4. That gives negative 13. U equals negative 5. So u equals 5 over 13. Then v equals 3 minus 25 over 13, which is 14 over 13. Now invert the substitutions. Since u equals 1 over 2x plus 1, we have 2x plus 1 equals 13 over 5, so x equals 4/5. Since v equals 1 over y minus 2, then y minus 2 equals 13 over 14, so y equals 41 over 14. Therefore, the solution to the original rational system is x equals 4/5 and y equals 41 over 14. The important idea was to set u and v equal to the reciprocals of the linear denominators, which turns the system into a simple linear pair. This method generalizes. For any system where each term is a constant divided by a linear expression, define new variables as the reciprocals of those linear expressions. You immediately obtain a linear system in the new variables. Solve it, and then invert to recover x and y. Example: we will solve a two-equation system that uses reciprocals. Here is the given system. Notice each equation contains the expressions 1 over x plus y and 1 over x minus y. Our plan is to make a clean substitution to turn this into a simple linear system. Step 1. Let A be 1 over x plus y, and let B be 1 over x minus y. Using these definitions, the original system becomes a simpler pair of linear equations in A and B. Step 2. We now solve this linear system. An easy elimination is to subtract 3 times the first equation from the second to get b equals 1. Then, a plus b equals 2 gives it equals 1. So, a equals 1 and b equals 1. Step 3. Replace a and b back into the definitions, keeping the same order. That gives 1 over x minus y equals 1, and 1 over x plus y equals 1. Step 4. Invert both equations. That yields x minus y equals 1, and x plus y equals 1. Final step. Add the two equations to get 2x equals 2, so x equals 1. Substitute into x plus y equals 1 to find y equals 0. Therefore, x equals 1 and y equals 0. In this example, we will solve a symmetric system of 3 equations in 3 variables using a clean invert plus add strategy. First, here is the problem statement. Step 1. Invert each equation and separate into sums of reciprocals. Start with the top equation, then the second, and finally the third. Step 2. Add those 3 results term by term. 2 over y plus 2 over x plus 2 over z equals 3, halves plus 4/3 plus 5/6. Factor out the 2 and simplify the right side. We obtain the key relation. 1 over x plus 1 over y plus 1 over z equals 11 over 6. Step 3. Solve each variable by subtracting the known pair from the sum. Using 1 over x plus 1 over y equals 3, halves gives 1 over z equals 11/6 minus 3, halves equals 1/3. So z equals 3. Using 1 over x plus 1 over z equals 4/3, we get 1 over y equals 11/6 minus 4/3 equals 1/2, hence y equals 2. Using 1 over y plus 1 over z equals 5/6, we get 1 over x equals 11/6 minus 5/6 equals 1. So x equals 1. Quick check. Plug the values into the original system. 3xy over x plus y becomes 3 times 1 times 2 over 1 plus 2, which is 2. 4xc over x plus z becomes 4 times 1 times 3 over 1 plus 3, which is 3. 5yz over y plus c becomes 5 times 2 times 3 over 2 plus 3, which is 6. All originals are satisfied. Therefore, the solution is x equals 1, y equals 2, and z equals 3. In this lesson, we will solve a symmetric system for x and y using a clean sum and product method. We will exactly follow the step order shown. First convert to sum and product, then combine the two equations, and finally extract x and y. Step 1. Define s equals x plus y and p equals xy. This turns both equations into simple relationships between s and p. From the first equation x, y times the quantity x plus y equals 20, substituting p for xy, and s for x plus y gives s times p equals 20. Solving for s yields s equals 20 over p. Next, from 1 over x plus 1 over y equals 5/4, rewrite the left side as x plus y over xy, which is s over p. So s over p equals 5/4, and therefore s equals 5/4 times p. We now have two expressions for s. Set 20 over p equal to 5/4 p. This gives 5/4 p squared equals 20, so p squared equals 16, and p equals plus or minus 4. Substituting back, s equals 5/4 p, so s equals plus or minus 5. Finally, recover x and y using the familiar quadratic whose roots are x and y. T squared minus st plus p equals 0. 4s equals 5, and p equals 4. The quadratic is t squared minus 5t plus 4 equals 0, which factors as t minus 1 times t minus 4 equals 0, giving t equals 1 and t equals 4. Therefore, the ordered pairs are 1, 4 and 4, 1, which solve the system. In this lesson, we will solve a system that came from an image. We will follow the exact algebraic steps shown there, line by line. Here is the system. We read it as x over 6 plus 4 over y equals 2, and 18 over x plus y over 2 equals 5. Our goal is to find x and y. First, we transform each equation exactly as shown in the solution image. For the first equation, x over 6 plus 4 over y equals 2 becomes the fraction xy plus 24 over 6y equals 2, which then gives xy plus 24 equals 12y. For the second equation, 18 over x plus y over 2 equals 5 becomes the fraction 36 plus x y over 2x equals 5, which then gives 36 plus xy equals 10x. Now, subtract the second final equation from the first final equation to eliminate the product xy. Doing that gives 12 equals 10x minus 12y. Next, we keep the linear relation and solve systematically. From xy plus 24 equals 12y, we get xy equals 12y minus 24. From 12 equals 10x minus 12y, we solve for x in terms of y, substitute back, and factor the resulting quadratic. This yields y equals 4, or y equals 5. 4y equals 4. The linear relation gives x equals 6. 4y equals 5. The linear relation gives x equals 36 over 5. So we have two solutions, exactly as the image suggests. As a quick check, substitute back into the original system. 6 over 6 plus 4 over 4 equals 2, and 18 over 6 plus 4 over 2 equals 5. Also, 36 over 5 divided by 6 plus 4/5 equals 2, and 18 over 36 over 5 plus 5 over 2 equals 5. Both ordered pairs satisfy the original system. We matched the exact structure from the image, transformed each equation, eliminated the product term, found a linear relation, solved via substitution, and reported both solutions. Great work! Here is the system. Step 1. Start with the first equation and isolate y. Write the first equation. Multiply both sides by y to clear the denominator. Collect the y terms on the left. Factor out y. And finally isolate y as 1 over 10 minus x. Step 2. Substitute this expression for y into the second equation. Start from the second equation. Substitute y equals 1 over 10 minus x. Clear denominators by multiplying through by x times 10 minus x. Simplify to a standard quadratic in x. Step 3. Factor the quadratic and solve for x. Factorization gives x minus 6 times x minus 4 equals 0. Therefore, the candidate solutions are x equals 6 or x equals 4. Both values are positive and satisfy the equations with y equal to 1 over 10 minus x. 4x equals 6, y equals 1/4. 4x equals 4, y equals 1/6. In the provided workflow, the positive x that is reported is 6. So we state x equals 6. Quick verification. 6 plus the reciprocal of 1/4 equals 10, and 1/4 plus 1 over 6 equals 5 over 12. Therefore, following the exact algebraic path, the reported positive solution is x equals 6. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.